Hello everyone, this is Shweta from AstronEra and welcome to Astro Stream with Ellen. Ellen Glad is my friend from long time ago and she is actually an optical research and development engineer in California, USA. And she has been doing these sessions with us and today is our fourth session with her about mining the moon imaging spectroscopy. Our next session is going to be about astrophotography for scientific applications on 28th of August. So if you are completing all these videos, all these lectures by Ellen Glad, you are going to receive a certificate. So if you haven't applied for a certificate yet, there is a form link in the description of this video, so you can go there and submit the form. If you have submitted once, that's fine. You don't have to submit it again and again. Also, at the end of this video, again, I'm going to have a little bit of announcement. So stay tuned until the end, and I hope you enjoy the session. Now, off to you, Ellen.
Awesome, thanks. Yeah, this is my fourth session that I've gotten to do here in AstronEra. My last session, I talked about black holes and galaxies. And this week we are talking about mining the moon, and I will get into that in a second and what that even means. In case this is the first time watching one of these, a little bit of background about me. You see some of my favorite pictures here. I really love astrophotography. That's a big hobby of mine. And I currently work at Millennium Space Systems as an optical engineer, where I get to do a ton of optical testing and building up our optics capabilities at our company. I graduated last year at Cal Poly San Luis Obispo in California. And so if anybody ever has questions about aerospace engineering at university or what it's like to work in the aerospace industry, please find me on Instagram at Ellen Glad Photo or find me over LinkedIn. Yeah, love to talk everything astronomy, astrophotography, optics, anything. So now let's get into it. So mining the moon. So this topic I chose because it was one that I got to really explore and dive into throughout my senior year at university. It was kind of our capstone senior design project for our entire graduating class. We had 70 people in our class, and we were divided into teams based on designing different space vehicles for a concept mission. So every year, this senior design project is different for every class. And as part of the simulation, as part of kind of preparing ourselves for the aerospace industry in the future, we had a fake customer that gave us a RFP, which is a request for proposal. And this is also commonly used in industry, where you do receive like a RFP from a customer, and then you make a proposal to see if they like your concept design for the satellite you're designing. And then we took this design through PDR, or preliminary design review. And this is one of many terms for a lot of industry standard different types of reviews. So the other common ones are you typically take, once you're accepted and once you're on a contract, you would start making your requirements for the system and go to a SRR, systems requirements review. Then you would go to this stage, a preliminary design review, and then a critical design review. And only after that would you actually start integrating and building the space vehicle up until a pre-ship review before you actually launch. So that's just a little bit about where those terms come from and how they're used. But so our project, our customer, asked for survey data on the moon, all of like what types of minerals are on the surface, what types of minerals are underneath the surface, how much can we know about the composition of the moon, as well as retrieval of these minerals, which seems pretty wild. And this was definitely an out there sort of project. The timeline was crazy, like pretending we were getting these minerals and analyzing them on Earth by 2050 or something like that. But this exercise, this meant that we had to create several different space vehicles for the different stages of the mission, which I'll talk about in a bit. But how this kind of relates to the topics we've been talking about so far, my focus on this was the payload of one of these space vehicles. So this Surveyor spacecraft that I worked on the concept for was this lunar orbiter concept to give information to the next space vehicles that would go and actually dig into or like physically dig into the moon and both prospect parts of the moon to see what minerals were there and eventually actually mine and retrieve the minerals and bring them back to Earth. So this Surveyor space vehicle was a lunar orbiter just to see what minerals we could get from any combination of a suite of instruments, whether it be telescopes, spectrometers, finding out what's the distance between you and the moon. That now require a laser altimeter or radar. So it was really all up to our team to decide how our suite of instruments would look to be able to fulfill the customer's requirements. And after a lot of trade studies and a couple months of figuring out what would be the best suite of instruments specifically to look at the minerals and to find certain minerals that the customer was interested in, we landed on a specific spectrometer suite to be able to detect these minerals from orbit. And that is what I spent a majority of my time really diving into and deciding how these spectrometers were going to be designed, how to size them, are we going to see these minerals, like what kind of spectrometers. So that's kind of background into what I'll be talking about. And this was one of our mission overview slides from a while ago. One of my friends made this really nice render of our space vehicle. But it just kind of shows launch, orbit insertion, the actual surveying portion, which is what I'll be focusing on. And as you can see, we ended up on this spectroscopy suite as well as a ground penetrating radar or GPR system. And that radar system was to actually get information on some of what was going on below the surface and try to see a little bit of the composition of the moon below while you're still in orbit. But again, I'll be focusing on the spectroscopy suite and then a bit about our communications. And these are a couple CAD models that another one of my friends created for this project. It just kind of shows you where the GPR antenna is, this like long flat thing, the spacecraft bus. We've got our communications dish on top, some solar panels for power, and then these 3 gold boxes on the bottom are the spectrometers that I helped size and design. And you can see the names of these: VNIR spectrometer, TIR, and SWIR. And I'm going to go into kind of what that means and how we chose what types of spectrometers and why we have 3 of them. So in spectroscopy, it really have to know what you are looking at and what features what you're looking at and what kind of minerals that you're trying to collect data on to know what types of detectors and what types of spectrometers you're going to use to look at them. Every type of substance and every mineral on the Earth has a specific spectral signature, which means that if you take spectral data of anything, even at work recently, my friend just for fun, took spectral data of an apple and an orange and like compared those spectral lines. And it was really cool to see, even something like that has a specific spectral signature. And you can characterize things by using spectroscopy. Whereas compared to just plain visual imaging, you just see picture data and what's available in the visible spectrum. And when you get into the world of spectroscopy, you open up a whole different realm of being able to characterize things when you can't exactly see the difference with your eyes. And this also applies for deep sky objects, like being able to characterize galaxies and nebula when you can't exactly see the difference with regular images. But I'll talk about that a little bit later as well. Anyways, so throughout the whole electromagnetic spectrum of light, and here you just see a portion of it from UV to thermal IR, you can perform different types of spectroscopy for every single one of these types of ranges. So you can perform visual spectroscopy or like with an imaging spectrometer, or you can do IR spectroscopy. And specifically in this region of the EM spectrum, you're mostly going to see absorption lines. But for this specific project, we knew we had specific minerals that we were looking for. The customer was interested in rare earth elements, platinum group elements, and gold. So because that was our job to find these specific minerals, I was doing research on what do the spectral signatures look like for each of those elements, and where do they show high spectral response. And that is what led me to highlighting these three different sections of the spectrum. So this really just depended on, where I was seeing high absorption lines and high response from the specific minerals we were looking for. And that landed us to create or to pick a visible and near IR spectrometer, a shortwave IR spectrometer, and a thermal IR spectrometer. And the reason these are separated and that you can just have one broadband spectrometer, although the flexibility in being able to choose different sizes for these different spectrometers based on like the individual wavelengths requirements, and also being able to choose different detectors for each of these wavelengths is really important. Some detector materials, if, for instance, like for your regular camera, a visible camera, either a CCD or a CMOS, if you're taking a picture of some object in space, it's probably going to have a silicon detector. And that's because silicon is very responsive in the visual wavelengths. Whereas when you go towards the IR side of the spectrum, you're going to want something like an InGas detector or a mercury, cadmium, tellurium detector. And these are just different types of materials that are combined into detectors to allow a lot of responsivity to these different materials or to different wavelengths. So this is how we picked the three spectrometers that we were using. And now a little bit more into kind of, I think you know which wavelengths we picked. This was sort of the overall spectrometer design, and this is a very general, like commonly used spectrometer design. So before you can kind of feed your light into the actual spectrometer part of your system, you still have to find a way to collect it and focus it. And this is why you still have a telescope system. It's not just the spectrometer. I think of a spectrometer system as just an add-on to, your standard telescope to still collect the light. So you have your incoming light. This telescope system could be either mirrors or lenses. A lot of times, if you're taking in light from several different wavelengths, if you're not just looking at one wavelength, then it's useful to have a fully mirrored system to reduce chromatic aberrations. Although if you're just looking at one wavelength, if you already have a light source that is just one wavelength, then you could get away with lenses as well. So this telescope system is going to focus the light into your spectrometer slit, and this is the beginning of the spectrometer portion of the system. And the job of the slit is to take in a tiny portion of the light, and the width of that slit is going to really affect your resolution of the light that you see on the detector at the end. The narrower the slit, the higher the resolution. And a lot of standard slits for spectrometers, you'll see like 14 micron, 25 micron, 50 micron, 100 micron. Those are like some common sizes. So really, really, really tiny. I've gotten to play with some like in our labs at work. And you can switch out different slits on systems to be able to see how that affects the resolution and see what you need to meet your requirements. But the downside in having higher resolution slits is that you're reducing the amount of signal coming in because you have a smaller physical aperture that's cutting off more light. So it's really a trade of how much resolution do you want, how much light do you want coming in. And once it goes through the slit, you are now just trying to image that slit onto your detector. So this goes to a collimating lens, and this collimating lens is going to collimate your light or make all the beams parallel. So if you think about like basically sunlight to us on the ground is nearly collimated because of how far away we are from the sun. But yeah, you'll need a collimating lens to parallelize the beams. And these parallel beams go to a diffraction grating. And this part's important because this disperses and separates the light into all its wavelengths. And every single individual wavelength will be separated, and that is what creates the spectral response or the like individual unique image that a spectrometer is used for. And all these different wavelengths fall onto the detector at the end. And that is what you see, the user, you'll end up with looking at an image of, or like a plot of absorption and emission lines from your light source. So now a little bit into sizing of the telescope, and this again is kind of that first portion of the spectrometer that's just focusing and collecting the light, which is important for how much light you're initially taking and what fields of view you're looking at overall. So for this project that I was working on, figuring out how big the telescopes were was important to figuring out the resolution that we wanted of the lunar surface. So to be able to size the aperture diameters, which is this distance all the way across the entrance of the telescope, we took the desired ground resolution that we wanted in kilometers and fed that into this equation along with the wavelength that we were looking at. So this wavelength changes from the visible spectrometer to the shortwave IR spectrometer to the thermal IR spectrometer, and the higher your wavelength is, you'll need a larger aperture diameter to see it. As well as taking into account how high up you are in altitude, your orbit altitude. And that is how you'll be able to size your aperture diameters. And it's great to have larger telescopes, but it's also, you want to conserve size on your spacecraft, and it's more expensive to have larger apertures. So it's, again, all a balance. And then the other thing I want to take into account is swath width. And this was important to consider and separate than just looking at the telescope, because field of view has to do with your camera sensor as well as your telescope. So taking into account the field of view that we wanted, as well as our orbit altitude, would give us how wide of an area over the moon we were looking at for a particular image. And this little graphic over here talking about kind of overall design specifications and how to characterize your telescope, your aperture diameter, which is this the length of your entrance diameter of your telescope, as well as your focal length, which often is the physical length of your optical system, unless you have a telephoto lens or something with a longer focal length that kind of makes it, that creates a longer focal length, but your system is not actually that physical size. But taking into account these two parameters, that is how you determine the speed of your system or the aperture of your system. This is also called the F number, and that's just the ratio of focal length to aperture diameter. So if you have a larger aperture, you're going to be taking in more light, and if you have a shorter focal length, you also will have a wider field of view. It's all about balance. And taking into account all those parameters and thinking about what types of sensors and detectors would be sensitive to these different ranges we were looking at, this was our final design of the spectrometer suite we were using to look at certain minerals. So you can see this short wave, or actually no, I'll start out with the visible and near IR spectrometer that was looking in the shorter end of the spectrum. We wanted a spatial resolution of 18 meters, and this, using the calculations that I just showed, gave us an aperture diameter of just about 1 centimeter, which is really small, but it worked out for what we needed. And the focal length was 4 centimeters, and taking the ratio of focal length over aperture diameter gave us an F number of F4. And to put that in perspective, a normal astronomy telescope that you might use for observing is usually around F10 or so. So F4 is going to allow a lot more light, and is a kind of a faster aperture, they call it. And the detector, we chose a silicon focal plane array because silicon is responsive to visible and near IR light. And for the shortwave IR telescope, similar spatial resolution was desired, but because of the spectral range and the slightly higher wavelengths, we needed a higher aperture or larger aperture diameter and a larger focal length, and this ratio was still the same of F4. But the detector changed because now we're looking at a little bit longer of wavelengths. So we have it's a Mercad-Tel, or a mercury cadmium tellurium focal plane array, and this is a common combination for IR detectors. We use the same detector for the thermal IR camera that we have here, and we needed a spatial resolution of 90 meters, and that reflected in a 2 centimeter aperture 8 centimeter focal length, and still keeping that F number of f4 because we wanted the same amount of light coming into each one. All right. So this plot I thought was cool to add because you can use, so that was kind of a use case for using spectroscopy for looking at lunar minerals, looking at minerals overall. But spectroscopy is used a lot in other parts of the astronomy community and a lot of astronomy research overall nowadays. And this is a plot of different spectral response curves of different galaxies. So if you were to take spectral imaging data of a handful of galaxies, you would be able to compare the spectral response curves that you get from each galaxy and characterize them based off that. So this blue line right here, this is a normal spiral galaxy's response. Obviously, they're all going to be a little bit different, but that's a kind of a general, the response curve is going to look something like that, where and these spiral galaxies are characterized by these strong emission lines, and this is because they have these young stars that are very emissive, very hot, and that's going to heat the surrounding gas. And also characterized by the absorption lines over here. Whereas compared to an elliptical galaxy, it's not going to have the same, I guess, like young stars as the normal spiral galaxy. So you see the strong absorption lines in the lower end of the spectrum here. So I thought this is a really cool plot of comparing these two types, and the comparison continues for other types of galaxies. And our own galaxy is a barred spiral galaxy, so I'd imagine it's something like a normal spiral, but possibly a bit different because of a slightly different type. And also going back to something that I think we talked about a couple weeks ago, red shifting versus blue shifting. You can also see that in this kind of spectral data. So a lot of galaxy spectra is red shifted, where the spectral features have shifted to longer wavelengths over time than the rest of the wavelength values. And some are blue shifted, where the spectral lines have shifted to the left of the spectrum if they are getting closer to us. So if you take spectra of galaxies over time, you can also analyze, is this galaxy going away from us, or is it getting closer to us based on the red shifting and the blue shifting? So lots of fun data you can get with spectroscopy. It's probably used might even be used even more than just plain visual imaging. And that's why a lot of the times on Spacecraft or just like spectrometer or imaging suites in general, you'll have a combination of visual cameras to get that data, but also spectrometers and other detectors to be able to combine all the data at the end and get the most out of your system as possible. So that wraps up my slides, and I will pass it back over to you.
Okay, perfect. All right, so we have many questions now. Can you switch back to your personal screen and stop the screen sharing?
Yeah.
Yes. Yeah, so we have lots of questions. Many are also generalized questions about the moon. So those who just want to take more information about the moon in general, we have a course on astronera.org exploring the moon. So you can just log into that and you'll get all the information about all the missions to the moon and everything about the moon. So go check that out, and we will answer the most relevant questions now because there are so many and we have less time. Okay, so Charu Agarwal is asking, lunar base operations might affect the moon's environment in adverse ways. Will it really lead to a bad and harmful environmental impact? If so, how? What can you say about this, Ellen?
And this is impact of, so I guess like these kind of activities, if we were to actually, go mine the moon, kind of what impacts that would have on the environment of the moon. Is that kind of
Yeah,
correct?
I think so. Overall, like what kind of impact it would have, and how if in any way it would change the relationship of the moon with the earth or stuff like that.
I see. So I guess the first thing, we looked into this a little bit. We were like, well, our customer like the fact that we are actually, taking away parts of the moon. How much mining are we going to end up doing? So definitely a concern, and that's a valid question. I think not for a long time. So what we found on our project was that the actual quantities of minerals that we were able to get with an automatic system. It's not people up there digging up minerals. With these spacecraft that we designed to kind of excavate the moon a little bit, we were getting extremely small amounts of material over time, and I think it would take a long time until it actually made an effect. And I'm assuming that question was kind of pointing towards the maybe like the tidal effects that the moon has on the ocean, or if the moon is physically getting smaller, how would that affect? So I definitely think yes, like over time it could definitely affect the environment, but I think not in a major way and not for a long time. Yeah.
Well, actually, considering how fast we are ruining the earth by mining it, I guess it wouldn't be such a long time if we, manage to get much stuff from the moon itself. So it might be possible that it might affect in a way, but yeah, it would probably take some time. Another question we have from Arnav Desai. He's asking, what is the most abundant element present on the moon?
So when we were doing a lot of our research, we found that so to our surprise, we found that the minerals that our customer wanted were not very, or there wasn't any evidence of a lot of these minerals on there. So we ended up looking for pathfinder minerals instead, or minerals that were commonly linked to these minerals that we were looking for. So if we were looking for gold, we were doing a lot of research into what minerals are found on Earth that are nearby gold or nearby these like rare earth elements, and what kind of minerals grow together. But that being said, it was a lot of silicates. We did find like a lot of evidence of iron, and that kind of led towards a couple of our pathfinder minerals. I think our platinum group elements. So yeah, we found iron hotspots, a lot of borosilicates, other silicates. Should have included like our map that we created. Let me see if I can.
That would be interesting to see if you have the map. So you're telling all these elements that came up in your observations, right?
Yeah, and this was in our research for kind of what is currently on the moon and what can we use currently to figure out which areas are we most interested in, where are we going to find the minerals that our customer is most interested in.
So also I have heard, just until you come up with the picture, I have also heard that the moon kind of smells like a gunpowder. Do you know anything about it? Why it might be like that?
Sorry, can you repeat that?
The moon smells like gunpowder. So do you have any idea of why that might be? I'm sorry, I've lost you. I lost you for a second there.
Oh no. But yeah, I actually haven't heard that before. That's really interesting.
So I think it is like that because I think it's a lot of friction from all the space debris falling on the moon, maybe because of that.
So I don't know if you can see, but yeah, I think that might be definitely an interesting thing. I'll have to look that up. But this was a like combined map that we created from what we knew already from researching. So you can see we marked different spots where we thought there were iron hot spots based on like present data, and also marking spots. Olivine was another mineral that we were looking into, and we kind of marked different concept landing sites that we would go to be able to go to these hot spots of minerals that we were interested in. But yeah, I thought that was interesting.
Yeah, absolutely.
But there's definitely more unknowns than knowns, and
yeah,
I think what we found was that we know less and less than.
Of course, imagine that. Like moon is the closest astronomical object to us, and still there is so much stuff that we don't know about it. That's fascinating. Okay, moving on to next question. Now this is from Amod Deshpande. He has asked so many questions and I hope we'll be able to answer them. But I'm going to ask a few that he has asked. So he's asking, can we fit the spectrometer to a telescope, like an additional lens to DSLR camera?
Good question. So if you had, like I have my camera and have my telescope, can I just attach a spectrometer to it? I think you could definitely, you could for sure integrate a spectrometer system into your physical system. It's because it takes a lot of, I think, precise alignment and where, you have to make sure your slit is exactly lined up for your light to come in from your telescope. And then that goes to a collimating lens that has to be precisely aligned as well. And then to your diffraction grating to disperse light on the detector definitely would take a lot of time and like precise alignment to put everything together perfectly. But if you already had, I guess, like an integrated spectrometer system, you could definitely, set up on a table, like you have your telescope over here, it's collecting some light in, and then it feeds into the spectrometer, and you would for sure be able to get data. So there are two, systems that you can put together, or you can just take light in general, walk outside, and if you're to set up a spectrometer, collect sunlight into the slit and see spectral lines on your detector. So there's definitely a lot you can do, and you can either break it down into components or sort of have it as a larger system.
Yeah, so continuing with that, I think Sandeep Nirgude is also asking how to make a spectrometer. What training do we need to make one? He's really interested to know how to make his own spectrometer, I guess.
Good question. So that is the thing. I have never made a spectrometer. That would be such a fun project. And now I'm trying to think, like, I haven't even ever looked up, like, buying the specific, like a diffraction grating. I guess you would go buy these specific components and totally, put them together. As long as you're feeding light into, a slit that's the correct size and feeding it through and having it go through a diffraction grating and putting on a sensor, then, that's going to work. You can definitely like play around with different types of detectors, different types of lenses, different sizes of slits, and making sure that you have the correct type of detector based on what light you're looking at and which wavelengths that light's in. You can for sure be successful with that. So that'd be a fun project.
Absolutely. I don't know about the high-end spectrometers, but I had once made a toy spectrometer and I had
Yeah.
learned it from a scientist. So maybe if I could find a link of how to do that with just the CD, you can make that a DVD. You can do a spectrometer. Like you just need a box and a DVD and you can make a spectrometer with that. So maybe at the end of this live stream, if I'm successful in finding that link, I'll post it either in the description or in the comment box of
Yes,
this
please.
video.
Yeah, I
So
want to talk to you about that.
yeah, that it's really cool. Like we do it for some school projects and then they really enjoy it. You can point it towards a tube light or the sun and you can definitely see the spectrum there. So that's interesting. Okay,
That's
moving
super
on to next question. Again, Amod Deshpande is asking, what is the minimum slit width in spectrometer?
minimum. So I know like a small or something that would be like a really high resolution. I've seen like 14, maybe 10, and maybe there's like a 5 micron slit. I'm not extremely familiar with kind of like what's the highest resolution slit out there. But those are common, like already 50 microns is a pretty narrow slit and will give high resolution, but I know there's options up to 25 or 14 and probably 10, probably 5. And then I guess like a maximum slit that I usually come across is like 200 micron or more. So somewhere in that range. And yeah, and you could also, again, make, whatever slit you would like and size it yourself as well.
Okay, perfect. So Charles Kepler is asking, how did the systems engineering look like to plan the integration of the spectroscopes you designed with the rest of the space vehicle?
Good question. So, yeah, so our team had to look at how our system or the system requirements for our spectrometers definitely combined with the other teams and like the thermal team, the power team, and trying to balance out how much power these spectrometers required. And that was sizing our solar panels. And the fact that, especially because our two IR spectrometers needed a cryocooler, which just kept the system cool to be able to reduce our thermal noise, that required power and more size, and was definitely a heavy power requirement for sure. It takes a lot of cooling to make sure your detectors in the IR region are not overheating and going to ruin your images from thermal noise. So those considerations were definitely taken into account. And also where to place your spectrometers on your spacecraft. So if you're putting your telescopes in an orientation where they're facing something that might be outgassing on your spacecraft, or something that might be particles might be coming off of it that you don't want coming into your lens, that'll also screw it up. So you want to make sure, if anything on your spacecraft is going to produce any sort of debris or contamination, that your telescopes are facing out on a part of your spacecraft that is away from that. So both orientation of where the things are and thinking about power and thermal requirements were the top kind of systems level things that we were looking at.
Okay, all right. So Amod is also asking, can we also observe anything else with spectroscopy, like cosmic background or something like that?
Cosmic background. Yeah, anything that is either showing emission lines or absorption lines, any sort of recognizable material or gas that's coming from something in space is totally going to show results. Of course, it depends on, once you get to a certain point, like far deep into space, your resolution might not be high enough, or you might not be collecting enough light to see that far deep into space. But if you have a super big aperture, and if you don't have constraints on that, and you are using a detector for the types of material and gas that you expect from those regions, then you will be very successful. So especially with like nebula and galaxies, and that that these regions are forming hot young stars and they're very active, then you're going to see emission lines in some of the IR regions telling you that it's like a very active galaxy versus like a not so active galaxy. But yeah, lots of fun things that you can do, and everything, or most, I think, if not all, deep sky objects will give some sort of like specific spectral signature.
Yeah, that would be really interesting. Like, I would love to see if cosmic microwave background shows any spectral evidences and how we can observe that.
Yeah.
Okay, perfect. So we have all right, we have many questions, but a lot of them are also unrelated to this talk. So actually, somebody is asking, Bhalura Guncha is asking, how does the life begin and evolve? And I think this question is better in our session with Reut, which is about astrobiology. And also there are very general questions like, are we really the star stuff? It's really fun how we say that the moon is not a star, it's a satellite. We know it as a fact. Even as humans, we are I mean, it seems so unrelated being on Earth, thinking that we are made up of star stuff, but it is true that everything has began from the Big Bang, and then the first stars were formed and everything started from there, and we are absolutely made up of star stuff. So actually, on such topics, guys, if you really want to know more about any other topic that you're interested into astronomy, you can actually let me know. Just put it in the comment box, and I will talk about it. I'm talking about it every Saturday. Every Saturday at 5 p.m. Indian time, I am doing a session called Ask AstronEra. So about these topics, I can speak for sure. Tomorrow as well, I'm going to talk about time travel. Lots of people are interested into that. So tomorrow I'll be covering that. It would be like, I think, my 5th episode. I have also spoken about why Pluto is not a planet anymore, or the recent Mars missions that we have sent, and whatever questions that you have in mind, you can just shoot my way, and I will answer them in these Ask AstronEra sessions. Also, as I told you about the spectroscope, the toy spectroscope, I will definitely put a link in the comment box of this video after this video ends, because right now while doing this I couldn't find the link, but I will make sure that you have that, because even Ellen is so interested. I can see her smiling. So yeah, I will do that. And also another announcement, as I promised you guys. So I mentioned Reut. Dr. Reut is actually an astrobiologist from Israel, and she is doing sessions with us just the way Ellen is doing now. We are going to have 5 sessions with her about astrobiology starting from 6th of September. So all your questions about the life in space, life elsewhere other than the Earth, she will be answering those. So make sure that you register even for her sessions and attend those. Even for that, you can get certificate if you have attended all the sessions. So I guess thank you so much, Ellen, again for joining us for today's session. And we are looking forward to our next session, Astrophotography for Scientific Applications, on 28th of August.
Super excited.
Yeah, it's going to be really exciting. Guys, if you have any questions about that, you can send them to us on Instagram, and we will make sure that Ellen gets them. and maybe in the next session she can answer them as well, because it's very wide topic, the astrophotography. So you can
Yeah.
surely, yeah. Ellen, do you want to
And
say anything else?
yeah, and I guess just to add to that, I'll try to, I guess I wanted to wrap up this kind of series with astrophotography because it's a huge hobby of mine, and I wanted to explain how it's practical in astronomy and what you can use it for, and kind of exploring all the useful parts of it. And that's not just for taking pretty pictures. But if you have any questions specific to DSLR astrophotography or a small telescope astrophotography, anything about camera selection, sensor selection, mount or tripod selection, those are all things I can would love to speak to. So yeah, and also let me know. Feel free to directly ask me any questions about today's talk, or if anybody wants to talk more about spectroscopy and imaging spectrometers, let me know. So
Yeah,
thank you.
our live chat is like flooded with questions, and people are really enjoying this session. And trust me, even I have enjoyed all of these sessions, and I'm really excited for the next one as well. So Shruti, actually you don't need to post it as many times. We see it once, and we will surely get back to you with the answers of your questions. And you all can go at AstronEra on Instagram, and you can find our Instagram channel where you can send us questions. We will make sure that Ellen gets them. Ellen, can you also tell your Instagram channel, the photography one? People are asking for that.
Yeah, that's Ellen Glad Photo, ELLENGLAD photo. And yeah, you'll find that there, and you can find my website and stuff like that.
Okay, perfect. I have also posted it in the comment box, Ellen Glad photo. So just search that on Instagram, and you can directly reach to Ellen as well. So yeah, Ellen, you're gonna be flooded on your Instagram DM now. Best luck with that. Awesome. So we'll see you guys next week now. Until then, clear skies. Bye bye.
Bye.